So this is the video where I'm going to describe a couple of examples of doing freefall problems. It's kind of a special class of problems that's typical in early physics education. And they all, honestly, they all run the same way and kind of have the same kinds of decision-making points. So freefall problems fall under the special situation kind of designation that I gave in an earlier video, where the acceleration does not change in time. It keeps a constant value. So freefall problems are the kind of problem where we get to use this generic formula. But I cautioned you that using this generic formula, sometimes people run into confusion trying to decide how to assign values and also assign whether or not to use a plus or a minus sign. So I'm going to try to address that in a simple starting example and then a slightly more complicated, involved example after it. So freefall just means that you're going to have an object fall with no sort of propulsion. And what I mean by that is like a rocket ship or a helicopter or a drone. Because they can sort of push against the air, they don't necessarily have a free fall situation associated with them. Yeah, I don't know. That's not really the best way to explain that. But anyhow, free fall in particular, like the thing that clues you into free fall is if the acceleration on the Earth, for example, is this 9.8 meters per second squared down. So yeah, this is going to be our acceleration value. There is no time dependence in this, so it's got this fixed value. And we have to make sure that whatever choices we make in the problem, when we get down to assign the value of the acceleration, we've got to make sure it points what we understand is down. Okay, so in this problem here, I've got a cliff and somebody stands out over the cliff and they let go of an object, and they are going to let it go without throwing it. They're not going to throw it up and they're not going to throw it down. They're just going to drop from rest. And this cliff is 58 meters above, say, the ground below, pretty far below. People tend to say, so we're going to use x of t equals to x naught plus v naught t plus 1/2 at squared. Except for, I'm going to do something. I'm going to change this into something that looks more vertical, because we are talking about the up-down position and motion of this rock or object that gets dropped. So y of t is an initial position on the y-axis plus an initial velocity in the y direction times the time plus 1/2 times the constant y direction acceleration times the time squared. It's just a change of the name of variables to reflect that's an up-down problem. So you have to make some choices even before you can get started. The first choice, honestly, is to realize that we are doing a freefall problem. And the result of making the realization is you get to choose that this models how this rock is going to be located at different places at different times. If it was not free fall, then you do not get to choose this generic form. That's one of the choices. Another choice is got to do with the coordinate system you're going to use. And the coordinate system choices involve two separate choices. One of the choices is where is 0. In particular, we're talking about where is y equals to 0. And the other coordinate system choice that's very important is which way is positive. So honest truth is it doesn't matter where or which way you choose for either of these, but you do have to choose somewhere. And for once you make choices here and you fill in the relevant quantities here, you do not get to make changes afterwards until you change problems. Okay, so I'm going to choose where the 0 is as the, I'm going to make a choice, doesn't really matter, as the starting point of the drop. So I'm going to identify y equals to 0 right here. And I'm going to say that the positive direction is up. So that's y equals to 0, and this is the direction in which y increases, and this is the direction in which y decreases. So I've made those two choices. So y sub 0 is the initial position of the rock at time t equal to 0. This actually is another coordinate system choice, is when is t equals to 0, the truth is. So I'm going to choose right here as t equals to 0, and when the rock reaches the bottom finally, that's some later time, and maybe that'll be a goal of our problem. Okay, so initial position of the rock is y sub 0, and that in initialness is right here. When is t equals to 0, it's right there. So initial position of the rock looks like, well, at time t equal to 0, my coordinate system says that the rock is at 0. So y sub 0 equals 0. So standard choice. Maybe I did it on purpose. Maybe you would do it on purpose later. Because you have to do a lot of example problems and homework problems before you get the hang of how things go and what ramifications your decisions give you. Okay, so I've got a choice, or this actually is a consequence of my choices up here. So v, the velocity in the y direction, initial, is supposed to be the initial velocity of the rock. It's the velocity at time t equal to 0, which I have labeled stopwatch time t equal to 0 is as soon as the person lets go of the rock. They just let go, that's when the stopwatch starts at 0. And the velocity, if you drop it from rest means that it starts with no motion. So not only is the initial position 0 according to my coordinate system, but the initial velocity is also 0 according to not really any of the other choices, but really about the choice of when was the stopwatch started. Okay, so the last choice is the choice of acceleration due to gravity, the number I'm going to put here. So this acceleration, it's got something to do with 9.8 meters per second squared, definitely, because it's the acceleration due to gravity, but I need to make sure that it is pointed downwards. So this is, if I look right here, the positive direction is up. So, but because the acceleration is downwards and up is positive, then down must be negative. This negative sign for the acceleration is a consequence of having chosen that the upwards direction is positive. So that means that the downward direction is the minus sign, and I have to do that myself. I have to be a physicist and choose the minus sign. So what this means is that y of t, which is the position of our rock for future times, is equal to 0 plus 0 times t minus 9.8 meters per second squared divided by 2, because there's the half, can't forget the half, times t squared. And then I can use this to solve problems. So you could ask, for example, when does rock hit bottom? So when does the rock hit the bottom? It's interesting. Let's solve this. So it looks like drop at t equals to 0, hits bottom at some later time. The question is, it seems to be, is what t is y of t equal to? So I want to know, how long do I need to wait before the value of y becomes something to do with that 58 meters height? So this is the position of 0 meters. So down here, this must be the position of y equals to negative 58 meters. So I want to know, at what time t is y of t equal to negative 58 meters? And this t is special, so I'm going to label it t star. At what t star is the position equal to negative 58 meters? So I go in and I've got y of t equals to negative 9.8 meters per second squared over 2 times t squared, right? And then y of t star is, everything's the same except for t is special now, and it has the value of negative 58 meters. Can you see that you can solve for t star, and you can see that the minus sign is going to go away, and I'll put the 2 up there and divide by the 9.8, and so t squared is that positive whatever results from it. So you can see that t star squared equals, so the minus signs cancel, it's a 2 times 58 over 9.8, so 2 times 58 meters divided by 9.8 meters per second squared. That's what t star squared is. You could fill in the algebra gap if you want. But let me do something. So this is 2 times 58, not 2.58. So let me put a little x there. So 2 times 58 meters. I want multiply or divide. Let me just rewrite it. So 2 times 58 meters divided by 9.8. So the thing about the meters per second squared on the bottom is, when you divide by a fraction, that's the same thing as multiplying by the inverse of the fraction. So this is multiplying second squared per meter. And the reason I'm doing this is because I'm making sure the units, so 2 times 58 divided by 9.8, meters divided by meters times second squared. So this is what the square of a particular time is, and so it better be units of second squared, and I just showed you that it is